Okay, so in this video, we are going to look at a slightly advanced part of doing vector analysis, which is how to manipulate indices. It's not really advanced in the sense of being difficult. It's very easy, in fact, and it makes a lot of computations in vector calculus very simple. I only call it advanced because generally this is not something that's taught at the BSc level. It's typically more of a master's level discussion. So for example, some of the problems that you might have been attempting either from Griffiths or from Shom series or one of these books on vector calculus, some of these problems might become much easier to do if you use this index notation. So let me just briefly introduce. I'm not sure how long this video is going to be, but hopefully not more than 20-30 minutes. Let's see. So the first thing I want to introduce to you, so suppose, okay, let's just start with the very basics. Let's say there's a vector, and let's call this vector A. So typically I would write it in terms of its components. So there's AX, which is the X component, and then there's AY, which is the Y component, and then there's AZ, which is the Z component. So AX, AY, AZ, the three components of this vector. Now what I'll do is, in general, I will label it as AI, where I can be either 1, 2 or 3, and these would correspond to, say, 1 corresponds to X, 2 corresponds to Y, 3 corresponds to Z. So I'll say the components of the vector, instead of calling them AX, AY, AZ, I'll call them A1, A2, A3. The advantage of calling it AI instead of explicitly saying AX, AY, AZ is that now I can easily generalize this to any coordinate system. When I say AX, AY, AZ, it means I'm working specifically in the Cartesian coordinates. But if I say AI, where I can be 1, 2, 3, then I'm not restricted anymore. I could choose a different coordinate system. I could say that 1, 2, 3 corresponds to r theta phi if I'm working in the spherical polar coordinates, or I could be working in the cylindrical coordinates, and I'll say I is 1, 2, 3 corresponds to s phi z, or whatever, any coordinate system that you're working with. I can just claim that my 1, 2, 3 stands for those indices. It doesn't necessarily have to stand for x, y, z. So in general, a component of this vector is AI, where I can be 1, 2 or 3. Now suppose I have two vectors. So I have A, and now I also have a vector B, which similarly has its own components, and we are going to call those components BI, where again I can be 1, 2, 3. Then how do you write the dot product of these two? You cannot see that. Components BI. Wait, you can't see that either. Very good. Where I can be 1, 2 or 3. Question is, how do I write the dot product of A and B? So normally you would say A dot B is AX BX plus AY BY plus AZ BZ. But since I want to write it in terms of 1, 2, 3, I'll say A1 B1 plus A2 B2 plus A3 B3. So I can say this is just summation over I of AI BI. Right? So this contains all three terms, where I can be 1, it can be 2, or it can be 3. So the summation I goes from 1 to 3. Now some of you who have done mathematical methods too, you've done some tensor analysis over there, and over there you talked about contravariant indices and covariant indices, or contravariant tensors, covariant tensors. So over there you made a distinction between whether you put the index downstairs or you put the index upstairs, subscript or superscript. Now that difference becomes relevant when we are talking about, let's say, something like relativity, where you have not just spatial dimensions, but you have 3 space and 1 time dimension. So over there, the difference between contravariant and covariant, or difference between lower index and upper index, becomes very relevant. Right now, for the time being, I'm just going to assume that we are just working in good old 3-dimensional space, R3. So I'm not going to bother with any notion of lower index, upper index. I'm going to put all my indices just downstairs like this. If this doesn't make sense to you, if you've not done that course, don't worry about it. Doesn't matter. You'll come across it at some point in future. So this is my summation AI BI, and now there is something called Einstein's summation convention. What this says is that if some index is getting repeated, like over here the index I is getting repeated, then you don't have to explicitly write down this summation. This summation is implied. So implied sum. So in Einstein's summation convention, I would just write this A dot B as AIBI, with the understanding that there is actually a sum over here, but I will not write it. So this is how you write a dot product using the Einstein summation convention. Now so what I'm doing right now is I'm just building up some of the basic ingredients, and then later in the end actually applying them to do calculations in vector analysis is going to be straightforward. It's just going to take a little bit of time to build up these basic steps one at a time. Okay. Now I want to make one important point over here. This I, we call it a dummy index. Maybe red is not the best color to use. Why is I called a dummy index? Because I in itself doesn't really mean anything. We are going to sum over I, right? So whether I called, suppose it was summation AI BI, I going from 1 to 3. This is A1 B1 plus A2 B2 plus A3 B3. Instead, what if I had called it J? So if I said summation J going from 1 to 3, AJ BJ, this also means the same thing, A1 B1 plus A2 B2 plus A3 B3. So the fact that we are calling the letter I doesn't have any significance. That's why we call I a dummy index. You can substitute a dummy index with any other dummy index. You can AI, BI, AJ, BJ, AK, BK, whatever. Any letter you want, any index you want, you can put over there. As long as it is being summed over. If you are summing over it, then it doesn't have any specific meaning of its own. It's a dummy index. Okay. Okay, so now I want to introduce two of my friends to you. My first friend, his name is Kronecker delta. Kronecker delta is written as a delta and with two indices, so ij. Again, all indices over here are going to run from 1 to 3. So I can be from 1 to 3, j can be from 1 to 3. So total there are 9 possible combinations: 1 1 1 2 1 3, 2 1 2 2 2 3, 3 1 3 2 3 3. Now, what is the definition of this Kronecker delta? Kronecker delta is defined as follows. It can be, its value can be either 1 or 0. And when does it attain these values? So it attains the value 1 when I is equal to j, and it attains a value 0 if I is not equal to j. So in other words, delta 1 1, delta 2 2 and delta 3 3 are 0, and all the other ones, so 1 2, 2 1, 1 3, 3 1, 2 3, 3 2, these are all 0. So basically the two indices have to be the same, only then it is 1. So let's do one possible example of how one uses this Kronecker delta. What if I was interested in calculating, so suppose I have some vector A, and what if I want to calculate delta ij ai, summation I going from 1 to 3. Now remember, we are going to use Einstein summation convention. So over here, since the index I is getting repeated, I actually don't have to write this sum. It's understood that I'm going to sum over I. So what's going to happen over here? So okay, first let's do it explicitly. So suppose j was equal to 2, just as an example. Then what would have happened? So I'm supposed to sum over all the i's. So this becomes, so I can be 0, I can be 1, I can be 2. So 0 2, not 0, sorry, 1 2 3. So I can be 1, I can be 2, I can be 3. So 1 2 3. But notice that delta 1 2 is 0 and delta 3 2 is also 0. It's only delta 2 2 which is 1. So this becomes just equal to A2. So when you multiply something with the Kronecker delta, what it does is it picks out just one specific element out of those, one specific component out of the 3 components of A. We can also think about it in more general terms. So if I did delta ij ai, so I can take all possible values 1, 2 or 3, but only when I is equal to j, whatever j may be, only when I is equal to j will that term survive. All other terms will become 0. So this is just aj. That's exactly what's happened over here. When it pulled out that component of a which was equal to this index over here. Similarly, over here it has pulled out that component of a which is equal to this index aj. So this is the Kronecker delta. Let's take one more example. Suppose I wanted to calculate delta ij ai bj. So there are two vectors now, a and b, and I want to evaluate this. Now notice over here there are two indices that are being summed. I is being summed and j is also being summed. So this is actually a double summation. There is a sum over I and there is a sum over j, which we are not writing because of the summation convention. So how would you do this? So over here again, as long as I is not equal to j, that term doesn't matter in the sum. It's only when I equal to j that this works. So when I is equal to j, this is going to be delta I is just 1 and then ai bi. And if you remember from the last page, ai bi is actually how we write the dot product. So actually what we've written over here, this delta ij ai bj, this is another way of writing the dot product. So these are some examples of how you use the Kronecker delta. My second friend that I want to introduce you to is called the Levi Chivita tensor. This is represented as epsilon I, j, k. This has three indices, I, j and k. How do you define it? So again, I, j, k can take values 1, 2, 3. You define it as follows. Epsilon 1, 2, 3 is defined as plus 1. Now, if I interchange any two indices, then I have to get a minus sign. So epsilon, if let's say I interchange the first two, so it becomes 2, 1, 3, then this becomes minus 1. Now if I interchange the last three, the second and the third one, so 2, 3, 1, then again I have to multiply another minus 1. So minus 1 becomes plus 1. Now if I interchange the first and the third one, so 1, 3, 2, then it will again pick up a minus sign. So every time you make an exchange of two indices, you have to make it negative of what it was before. There should be two more combinations. No, there should be 6 combinations total. 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1. Okay, let's try and bring 3 first. So let's interchange the first two. So it becomes 3, 1, 2. So this becomes plus 1. And now I'll interchange the last two. So it becomes 3, 2, 1, which is minus 1. So one way to think about it, and this is true only when you have 3 indices, is if you take a cyclic rotation of 1, 2, 3. So 1, 2, 3, 2, 3, 1, 3, 1, 2. These are plus 1. But if I do an anti-cyclic rotation, so instead of 1, 2, 3, if I take 1, 3, 2, or 2, 1, 3, or 3, 2, 1, then this is minus 1. If any of the indices repeat, so if I have epsilon 1, 1, 2, or epsilon 1, 2, 2, or epsilon 3, 1, 3, anything like that, any repeated indices, then it becomes 0. And of course, we are going to use this also in various kinds of summation calculations, just like we did for Kronecker delta. So let's take one example. Let's evaluate epsilon I, j, k, a, j, b, k. What is this? So again, this is a double sum because j and k are both repeated indices. So I'm going to sum over them. What is this? So this is going to be, let me take specifically for the case where I is equal to 1, epsilon 1 jk. Let's see what this turns out to be. So j and k will both run over 1, 2, 3, 1, 2, 3. So there are total 9 combinations. So epsilon 1, so let's take 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. Now see, most of these are becoming 0 because there is a repeated index. 1, 1, 1 repeated index, 1, 1, 2 repeated index, 1, 1, 3 repeated index, 1, 2, 1 repeated, 1, 2, 2 repeated. This survives, 1, 3, 1 repeated, 1, 3, 2 survives, 1, 3, 3 repeated. So all of these became 0 because one of the indices is repeated. What I am left with is epsilon 1, 2, 3, A2, B3 plus epsilon 1, 3, 2, A3, B2. Now epsilon 1, 2, 3 is plus 1, epsilon 1, 3, 2 is minus 1. So this becomes A2, B3 minus A3, B2. Does this look familiar to you? Does this remind you of what happens when you take a cross product? Because when you take a cross product, suppose you took A cross B, then you would write I, J, K, and then A1, A2, A3, B1, B2, B3. So this would be I, and then you would get A2, B3 minus A3, B2, and then plus J, A3, B1 minus A1, B3, and then similarly for K also. So what we have got over here is just the X component, or rather the one component of A cross B. So this is actually the definition of cross product using this index notation. So if you take a cross product A cross B and you want to find out what is the I component of this, where I can be 1, 2, 3, then this is defined as epsilon ijk aj bk. And A dot B we saw was just AI BI. So this was the Kronecker delta and the Levi-Chivita symbol. The last thing that I want to tell you is how to relate these two, how to relate the Levi-Chivita symbol and the Kronecker delta. And that expression, and I'm not going to prove it, you can probably just try out different combinations and verify that it works. If I have this epsilon ijk epsilon ilm, this product, and remember there is a sum inside this because I is a repeated index, so you are summing over these, then this is given by the following: delta jl delta km minus delta jm delta kl. So you're summing over I. So on the right hand side there is no I. So first index and second index minus first index, second index, first index. That is how. And this is the formula that we are going to be using most often. So these are all the basics that you need to know for how to manipulate indices. Let me introduce one slightly different thing: the vector operator. So you've seen this del in vector calculus, both in math methods and in electromagnetism. Oh, and in classical mechanics. So you've seen this multiple times. So this we saw was I d by dx plus j d by dy plus k d by dz. So each component of the components of this operator are d by dx, d by dy, d by dz. So this we refer to as del I. Again, I goes from 1 to 3. So if I say del 1, then that is with respect to x, del 2 with respect to y, del 3 with respect to z. Or of course, it could be, you could be in some other coordinate system. So del 1, del 2, del 3 could correspond to del r, del theta, del phi, or whatever it is. So we are going to treat this also the same way as we treat the components of these other vectors when we are doing our manipulations. So okay, so now all the cards are on the table, and we can try and actually calculate some identities in vector calculus. So I'll just show you a couple of them, and with the help of these basics you can then attack any of the other ones that you might have seen. So the first one I'll talk about is the vector triple product. So now we are looking at applications of whatever we've seen so far. And you will see that, of course, in the beginning it might be a little hard for you to get used to this kind of calculation. But once you practice, you'll find that instead of doing pages on pages of tedious calculations with the x component, y component, z component, in like 5-6 steps you can get those same results. So let's take the vector triple product. Which is A cross B cross C. And this is given by the back minus cab rule. What is that? I think it's this. Is it? Let's see. We'll work it out and see if we get this. So because this is a vector quantity, I'm going to try and find out the ith component of this one. And remember, I can be anything. It can be 1, 2 or 3. Ith component of LHS. Now LHS is a cross product. It's a cross product of A and this other one. So the ith component of this is epsilon ijk aj, and then this other vector k. And now because this is a cross product, I can further split this also. So I'm going to keep everything else intact. And this becomes, what is the k component of B cross C? It is epsilon k lm bl cm. So same thing, any cross product you write like that, as epsilon, then first one, then second one. And you have to match the indices appropriately. So let me just rewrite this, epsilon ijk, epsilon klm, aj, bl, cm. Now remember that from the properties of this Levi-Chivita symbol in 3 dimensions, you can do a cyclic rotation and keep epsilon the same, or you can do an anti-cyclic rotation and change its sign. So over here, what I'll do is this first one, I'll just rotate it cyclically. So instead of ijk, I'll call it kij. That's a cyclic rotation. And I just did that because I wanted to keep the k's in the beginning. I wanted both the k's at the starting so that I can apply this identity of ours. because this identity only applies when the first index is the same. So let's then apply that identity. This becomes first with first, second with second, minus first with second, second with first. So, okay, now because this is the first time, I'm going to explicitly open everything and write it. So this is delta IL, delta JM, AJBLCM, minus delta IM, delta JL, AJBLCM. Now what? If I look at this first term, because the delta is there, remember delta always forces the other index to take on its own index. So delta IL will force all the L's to become I's, and delta JM will force all the M's to become J's. So this becomes AJ. BL has been forced to become BI, and then there is CJ. M has been forced to become J. Minus, in the second term, delta IM forces the CM to become CI, and delta JL forces the L to become J. So AJBJ. So this is, so BI. What is AJBJ? AJBJ is just A dot C. And similarly over here, minus CI. What is AJBJ? That is A dot B. So as a result, what we have shown is that the ith component of the LHS, so A cross B cross C, this one's ith component is basically the ith component of B with A dot C minus the ith component of C with A dot B. But you showed it for the ith component, means this is true for the x component, this is true for the y component, this is true for the z component. So this is true for the entire vector. So that just shows that A cross B cross C is just B A dot C minus C A dot B. So component wise we have showed that this is true. So we verified this vector triple product. You can imagine the same thing if you had to prove doing explicit calculation. You would have taken A dot C as AX BX plus AY BY plus AX BX plus AX CX plus AY CY plus AZ CZ. Similarly, A dot B would be AX BX plus AY BY plus AZ BZ. Then you multiply those with the B vector or the C vector, then you subtract them, etc. etc. Similarly, left hand side also would have been a complicated calculation. Instead over here, just in a few steps, and right now I've done everything explicitly. Once you get used to it, within 3 or 4 steps you'll get the answer. So this considerably simplifies the kind of calculation that you need to do. We should take another example. What other example should I take? 1 second, let me check the book. Okay. So let's take one more example. Let's prove that divergence of curl is 0. So I want to prove that for any vector A, this is 0. How should we go about doing it? So over here we are going to write this, we are going to use this del I notation for the derivatives. So now you can think of this as being a dot of del and this other one. So the dot product is written as del I, and this other one also I. This is the definition of dot product. Now what is this? This itself is a cross product. So I'm writing the ith component of this. So this becomes epsilon ijk, the first one j, the second one k. So this is epsilon ijk del I del j ak. Now something very interesting happens over here. Let me call this equation 1. Now remember, I and j are dummy indices because I'm summing over them. So it doesn't matter what I call them, right? Instead of I could have called it t. Instead of j, I could have called it c. Any index I can put, no problem. So same way, if I can call it anything, I can rename them. Then I can call I as j and j as I. It doesn't make any difference. So I can write it as epsilon j I k del j del I a k. Now derivatives with respect to j and I, they commute. In general, whether I take derivative first, partial derivative first with respect to x, then with respect to y, or I take first with respect to y, then with respect to x, that order doesn't matter. So delta j delta I can write simply as delta I delta j, no problem. But what I have over here is epsilon j I k, and if I interchange any two indices, then I pick up a minus sign. So let me interchange the first two. So if I make it epsilon I j k, then I have to pick up a minus sign. And I'm going to call this equation 2. Now look at equation 1 and equation 2. I have LHS is equal to epsilon ijk del I del j ak. But that same LHS is minus epsilon ijk del I del j ak. So this LHS is equal to minus LHS, meaning LHS has to be 0. Therefore, divergence of curl is 0. Let's take one last example. I'm going to prove that divergence of A cross B is B dotted with curl of A minus A dotted with curl of B. Let's prove this identity and see. How should I do this? I think I'll have to do LHS RHS separately. Okay, so let's take LHS. This is like a dot product. So del I and then I of the other one. But this is a cross product. So I'm going to write this as del I epsilon I j k a j b k. But epsilon is a constant, so I can take that out of the derivative. very good. This might actually work out directly from here. Now derivative of product is just, you can use the product rule for derivatives. So this becomes equal to epsilon ijk aj and derivative of bk plus bk and derivative of aj. So let's break these up. So I get aj epsilon ijk del ibk plus bk epsilon ijk del iaj. Now there's a little bit of rearrangement. So now you can see that this is already starting to look like a cross product. This is also already starting to look like a cross product. So what I'm going to do is I'm going to rearrange the indices of the epsilon in such a way as to make this exactly a dot product. So if I want this to be a dot product, so I have del I bk, then I should bring the j in front. So let's interchange the j and I, and that will pick up a negative sign. Similarly over here, there is I and j at the end. So if I cyclically rotate the ij case, then I will bring the k in front. Now this has become a cross product, this has become a cross product. So this is minus aj. What I have over here is the cross product of del and b. So del cross b, and it's a jth component. Similarly over here, what I have over here is the kth component of the cross product of del and a. And this is just dot product because aj something j or bk something k, same index. So this is minus a dot curl of b plus b dot curl of a. And that is exactly what the right hand side is. So you can see in 5 steps we have managed to derive that result. So here you go. This is the general method. Using indices, you can, in a very easy manner, without doing a long calculation, you can prove all of these vector identities. So I invite you, there are many more rather ugly problems in vector analysis, and one of them I actually gave you as part of your assignment 1. Try solving that using index notation and see if that method is much easier than what you have done. I'm not going to accept this result for the assignment. I want you to do the full calculation, because when you're starting to learn vector calculus, it's a good idea to see exactly how those calculations come about, what are the steps that go in there. So I want you to do the full calculation. This is just for some little extra information for you. Okay, so we'll stop here.